So in this video, Other Molecular Shapes, we're going to take and expand upon the 5 basic geometries. So the 5 basic shapes are related to steric numbers. And so the steric numbers are SN2, linear, SN3, trigonal planar, SN4, tetrahedral, SN5, trigonal, bipyramidal, and 6, octahedral. And so we're going to look at what happens when instead of there being 2, 3, 4, 5, or 6 atoms connected to the central atom, instead, we're going to start to see a lone pair. And so one of the things you'll notice is that we're really only going to look at these structures in the tetrahedral, trigonal, bipyramidal, and octahedral structures. In a linear structure, it's still just going to be a line. And what we don't see is a steric number of 3, typically with 2 bonded atoms and a single lone pair. Doesn't mean it doesn't exist, but it's very rare. So the lone pairs are going to compress the remaining atoms. So if we think about ammonia, NH3, we can draw a Lewis dot structure of this, and that tells us it has a steric number of 4, right? We have a lone pair and 3 hydrogens. The question is, how does this lone pair affect the bond angle between these? So let's start looking at the steric number of 4, or the tetrahedral, first. So there are other molecular shapes. And so we're going to start by looking at, so we started with the AX4, which is these are going to be a little cramped. And this is tetrahedral. We're going to look at the AX3E, where E is a lone pair. We're also going to look at AX2E2, where A is our central atom, X is our terminal atom, and E is a lone pair. So for AXE, in that case, we're going to look at NH3. So let's go back to the ammonia structure that we drew. Oops. We have the N and these 3 hydrogens. Because it has a steric number of 4, we know that the base shape is tetrahedral. So we can start by drawing our nitrogen and connecting it to the traditional tetrahedral shape. We just only have 3 hydrogens and a single lone pair, which I put on the top. It could be on all of them. If we imagine, in this case, that this lone pair cloud is much bigger than a hydrogen atom, this is going to effectively push all of these down. And so what we're going to see is a contraction of this bond angle, where this has reduced to 107 compared to the tetrahedral of 109. So this angle is 109.5, and then AXE, where this is a lone pair, what we see is a bond angle of 107. And so this shape is actually called trigonal pyramidal. And so when you're asked to draw something, you would determine the steric number, then determine what the molecular shape is. So the molecular shape is different than the base geometry. In this case, if you were to look at this structure and not be able to see the lone pair, which we can't see electrons, what you would see is this, where these are contracted. And so the shape just kind of looks, you kind of got to go with it here, like a trigonal pyramid. Not a great pyramid, but that's what it looks like. So we are going to draw the lone pairs to remind us how the structure looks like. So let's look at one with AX2E2. So water, or H2O, is a good example. where we have a Lewis dot structure that looks like this. And based on this structure, you might expect for the hydrogens to be 180 degrees apart. So when we count the number of things connected to the central atom, what we see is 1, 2, 3, 4. So this also has a steric number of 4, which means that it has a base geometry of 4, of tetrahedral. So we're going to draw our oxygen in the center. We're going to have 4 things connected to it. 2 hydrogens, 2 lone pairs. I'm going to put my hydrogens in the plane of the board. You can put them anywhere you like. These 2 electron clouds would like to be as far apart as possible, and that is going to contract this even more than the previous 107, and it's going to go down to 104.5. So when we draw this structure, if we put our x's here, we see a contraction of 104.5 and 2 lone pairs. So this structure, its name is bent. Because if you only saw the oxygen and the hydrogen, what you would actually see is something that looks like this, which is more compacted than it would be if you only saw part of the tetrahedral molecule. So there are 4 tetrahedral. There are 3 shapes. For AX4, it's tetrahedral. For AX3E, it's trigonal pyramidal. And AX2E2, this is bent. And so you need to know how to draw the structures, what do the structures look like, and how are they arranged in 3D space. So now that we've thought about the steric number of 4, let's take a look at maybe steric number of 5 and 6. So in steric number of 5, we're going to look at the base shape of AX5, which is the trigonal bipyramidal, and it looks like this. And so when we look at this structure, what we can see is that there are 5 different places where we could remove a single pair of electrons. So the question becomes, which one gets lost first? Because they're not necessarily the same. Don't forget that we have the equatorial and the axial. At the end of the day, we want the electrons to be able to have the most amount of space possible. So in the AX4E, an example of which is SF4, where we have a Lewis dot structure that looks like this. So we have a steric number of 5, but how does this structure change from the trigonal bipyramidal? The lone pair needs to take up as much space as possible. And so it's going to need to be in the equatorial. And these are backwards. So let's scratch that out. We have equatorial along the center and axial at the top. And so in this case, this lone pair here needs to be in the equatorial plane. So we start by drawing our base geometry of trigonal bipyramidal. And the lone pair needs to go in one of the equatorial positions. Traditionally, it is drawn in this one. They are all the same. You could draw it in any of them. So as we draw our fluorines with their lone pairs, we can see that this structure is slightly different. So the name of this is seesaw, which is a little hard to visualize unless you turn this molecule on its side. And so when you turn the seesaw on its side, what we see is this. And I'm going to leave out the lone pairs just for brevity. And so what we see is a sulfur, or you could imagine that these two ends teeter-totter back and forth, or it's a seesaw. So for AX for E, it's seesaw. So I'm going to go ahead and draw that down here. So we have AX5. And it looks like this. And we see 90-degree angles and 120-degree angles. For AX, AX4E, we have the A in the center, the same base geometry with the E or the lone pair here. And it turns out that what we see is a slight compression where this is slightly less than 90 and this is slightly less than 120. And this is called seesaw. Where this one is trigonal bipyramidal. So once we have this information, let's go back up and let's start looking at AX3, E2. So in this case, we're going to look at BRF3, which has a Lewis dot structure of this, with all of its lone pairs hanging out. And bromine actually has two sets of lone pairs on it. So these lone pairs need to be as far apart as possible. It turns out that the furthest apart they can be is actually going to be in the equatorial plane, even though it feels like it could also be in the axial plane. But what we have found experimentally is that the structure looks like this. We have a bromine in the center. We have our base geometry. And put our fluorines, and the third one goes here. We have our two lone pairs in the equatorial plane, and so this is also slightly less than 90, but it allows the electrons to have the most space possible without being interfered upon by the other elements, and this is called T-shape. And so our last example, and then we can go ahead and add the AX3E2 gives us the X's here in a T shape, followed by the two lone pairs, and we have slightly less than 90, and this is called T shape. The last one we'll see in this pool is AX2E3, and so let's look at an example for that. For AX2E3, a good example would be xenon F2. So now we're going to draw a Lewis dot structure, which has our xenon in the middle, connected to our two fluorines, which use up many of the valence electrons. And it turns out that xenon has 3 lone pairs left. So now we would like those to be as far apart as well as all the atoms. So when we draw our structure, you'll notice that all of the base structures look the same. So if something has 5 things connected to it, we start by drawing the base tetrahedral or the base trigonal bipyramidal. Then we figure out the arrangements of the atoms and the lone pairs. In this case, our two fluorines are going to go along the axial axis, and our 3 lone pairs will be here. And this is linear. And you can see that because if you can't see any of the lone pairs, this XEF2 structure is identical to an steric number of 2 structure. So they all have the same name with the same shape. So AXE2 gives us, we have an A in the center with our lone pairs in all of these. And this structure is 180 degrees, and this is considered linear. So we can see all of the different base shapes when we look at the steric number of 5. So steric number of 6, octahedral, remember, has 90 degrees between each of them. So when we look at A, This is our base octahedral structure. So we are going to look at removing one electron or one atom and replacing it with a pair of electrons at a time. So we're going to start with AX5E. So it turns out that when they all are the same, the first one you remove doesn't matter structurally. So if we look at BrF5, we have our bromine in the center connected to 5 fluorines with all of its lone pairs. Whoops, that's an E. And then once you've used all of your valence electrons, we have a single pair left here. So it gives us this steric number of 6. So as we look at this, we put together the bromine in the center. We're going to draw our base octahedral. And then we need to put in the fluorines as well as the lone pair. Traditionally, it's drawn on the bottom, although it can go on any face because they're all identical at this point. So we're going to put our lone pair here, draw in our 5 fluorines, and they're very multiple lone pairs. And so here, this shape is considered to be a square pyramid. And so if you remember that the degrees in this were all 90, what we actually see here is slightly less than 90. The lone pair just compresses everything slightly forward. So we can draw these down here. So if we have the AX6 and the AX5E, followed by the AX4E2, AX3E3. So in this case, for our base octahedral, we have our A in the center, followed by the 6. We have octahedral. For this one, we have the same base structure. And so you could rotate this in any direction. So let's look at one where we have removed another 2. Oops, sorry, this is square pyramid. So let's go back up here and look at AX4E2. So we're going to have our base structure, and we have XeF4. So our Lewis dot structure puts xenon in the center with its fluorines, with all of its many lone pairs. And there are 2 lone pairs left over. So in the base octahedral structure, where we have xenon in the center, what is the arrangement that would allow the lone pairs to be as far apart? It turns out that they need to be 180 degrees apart. So we could put them on this axis, or this axis, or this axis, as long as they are 180 degrees apart. So I'm going to put them on the green axis, although it is indistinguishable from the other 2. So we have our lone pairs here, and our fluorines on the other. And so the structure, the name of this is considered square planar. And so in this case, we can redraw that here with that same base geometry. So if there are 6 things, you're going to start by drawing a base octahedral. We're going to put our x's along here and our lone pairs top and bottom. And so this is square planar. So then we can look at AX3E3. And so when we draw this structure, we're going to put our A in the center. And now we need to figure out where the lone pairs go. We want them to be furthest apart. And so that would be to put them along 3 of the 4 in a single plane. And so we're going to put our x's here and this is considered T-shaped. And while there are very, very few structures of AX to E4, in that case, what you would have would be the A in the center, your X's along any of the axes, and all of your lone pairs along the central, and that would be linear. So I will go down and draw these in our regular structure. And so for the AX3, E3, we have A followed by our structures. We're going to put our X's first this time, making sure they and the lone pairs are furthest apart, and this is T-shaped. And so this angle is slightly less than 90, and if you have A, X2, E4, you have an A in the center, and your two X's will be along any axis with your lone pairs everywhere else, with the bond angle here being 180 degrees, and this is linear. So if we look at all of these, we can clearly see the arrangement going from a fully structuralized all the way to having mostly lone pairs. So to determine the molecular geometry, first you're going to draw a Lewis dot structure. An accurate Lewis dot structure is going to allow you to determine the base geometry and the molecular shape. From your Lewis dot structure, you will count the number of things, whether it is lone pairs or atoms, connected to the central atom. This will identify the base geometry. Your options are 2, 3, 4, 5, and 6. Once you do that, you can figure out how many lone pairs are on the central atom to determine the molecular geometry. And this is important. You must memorize the names of the shapes, the base geometries, how to draw the shape, and the bond angles. In the next video in this series, we're going to work several examples. There are also handouts in the information online that you can access that will give you more insight.